Hello and welcome to today's webinar. This is part 4 of a webinar series dedicated to the use of ATR, FTIR spectroscopy in academia. The objective of the webinar is to give you an update on the most recent scientific publications showing how researchers in academia use React-IR creatively to uncover reaction mechanisms, understand kinetics, and identify reaction intermediates. This is actually part 4 of a series that started about a year ago. If you haven't got a chance to watch the previous webinars, you can get them on demand for free on our extranet, also called the community website, or just send us an email, type in the chat box, and we'll send you the link. Now, going forward, we'll probably have such an update once a year. We try to focus on the most recent papers, and we also have dedicated webinars to give literature updates from the pharmaceutical and chemical industries. Alright, if you are new to real-time mid-infrared spectroscopy and would like to have the technology demystified, this is definitely not the right webinar for you. Indeed, I do not have a single slide on the technology itself. It's all focused on case studies picked up from the recent scientific literature. We do have some excellent webinars though on the technology work and how you can use in your laboratory. I listed here a few of them, and again they are available on the extranet, or you can get them on demand. Just send us an email. Finally, today's tip is that you can also type React-IR on YouTube and you get access to outstanding videos about the React-IR technology. Alright, now I'd like to get down to the core of the webinar and show you the papers I selected. I have 6 papers divided in 3 categories. The one I would like to start with covers metal-catalyzed chemical transformations. The first example is from Hugh Davis and colleagues at Emory University in Atlanta, Georgia. It was published last year in the JOC. The general topic was to evaluate the catalytic activity of heterobimetallic bismuth rhodium complexes towards metal carbenoid chemistry, and to be more specific, towards cyclopropanation reactions. Another goal was to compare the performance of bismuth rhodium to rhodium-rhodium complexes as far as selectivity and reactivity. An important point I want to make here is that this example, like the following ones, my goal is not to go into the detailed scientific findings. I would strongly recommend that you go and read the publication for this purpose. My goal here is to highlight the context in which FTIR real-time reaction analysis was used, what the challenges were, and how React-IR helped meet those challenges and answer key questions. Having said that, let's go to the results of this particular paper. The waterfall plot I'm showing you on the bottom left corner represents the disappearance of the diazo stretch frequency at 2100 wave number. As you can see on the equation displayed on the top left, the diazo reagent is reacted with styrene and yield a cyclopropane product. If you look closer, the waterfall plot on the left actually shows a very fast reaction done in a fraction of the 56 seconds window displayed here, and I circled in green. 0.2 mol% of catalyst was used, which corresponds to a turnover frequency of TOF of about 30 seconds to the -1. Now, by comparison, on the right side we have the bimetallic complex rhodium bismuth 3, which under similar conditions get the reaction complete in about 45 minutes, so much more slowly, less reactive catalyst. Again, figuring out how long it takes to reach reaction completion is extremely easy using the 3-dimensional surface as shown on the top right of this slide. Alright, in conclusion, what I really like in this paper has to do with the possibility to directly monitor the rate of diazo disappearance using React-IR, a probe actually immersed in the reaction mixture. We saw the very simple visualization of concentration decrease when the reaction takes 45 minutes, But much more amazing is that the same can be done when the reaction took only 16 seconds. In such a case, React-IA can be used in a fast scan mode and collect a spectrum down to every second. This makes it a great and unique tool to track fast reaction. The next paper I'd like to show you comes from Vito Capriati and Saverio Florio and colleagues at the University of Bari in Italy. This work was published in JACC in 2008. I really like the fact that it goes to the heart of using spectroscopy not just to monitor a chemical reaction, but to help gather clues as to what the reaction intermediate might be. It covers the use of in situ IR and NMR spectroscopy to get a better insight into the stability of the lithium salt shown on the top right of your screen. Previous studies had shown seemingly conflicting results. On the one hand, the salt would racemize extremely fast at very cold temperature, which was corroborated from computer modeling. On the other hand, the same molecule was observed to be stable at -78 degrees C for hours during a deuteration experiment. So the key question was the following: is the lithium salt obtained from reacting structure 1 with a very strong base in THF at -100 degrees more like an organolithium, or is it more like a NASA enolate, like shown on the top right of your screen? In situ IR spectroscopy gives interesting clues here. As the deprotonation occurred, the two bands corresponding to the starting oxazolidine moiety at 1660 and 1678 wave numbers disappeared, while a band at 1600 wave number emerged. Based on literature data, if we have an alkylidene epoxide, like the structure on the upper right, we would expect a band more in the 1750-1800 wave number region. In other words, having a shift down only 60 wave number tells us that what's happening here is more consistent with the formation of the organolithium derivative lithium-1 as shown on the top right of your screen. Now, if you wonder how fast this reaction occurs, the answer is extremely fast. It doesn't take more than a minute for all of compound 1 to disappear, which can be seen by profiling the bands corresponding to compound 1 and its lithiated equivalent as a function of time. In conclusion, what I really like about the paper is that it's a little bit like a detective game where you have to search for clues and solve a mystery. So thanks to its functional group specificity, in situ mid-infrared spectroscopy allowed to gather clues in favor of the formation of species lithium-1 rather than a suspected ASA enolate. C13 and lithium-7 NMR were also used to further investigate the reaction intermediates, as you can see on scheme 5 shown on the right side here. Let me now move to the third example of this metal-catalyzed reaction category. It covers a paper from Aiwon Li at Wuhan University in Beijing in China, and this paper was made in collaboration with Metal-Catalyzed. The chemistry is about Palladium-Catalyzed cross-coupling between a halo alkyne 1 and a terminal alkyne 2 to form diene 3. I made the reference available at the bottom of the slide. The goal of in situ FTIR spectroscopy here is to measure reaction rate under various conditions and get an insight into a reaction mechanism. As an aside comment, there is also a paper in Orglet from the same authors describing a Negishi coupling using the same mechanistic approach. Alright, now going back to the paper, you can see on the left figure that the bromoalkyne 1 and the product 3 have unique absorbency at 973 and 955 wave number respectively. So as you can see on the figure to the right, trending those bands against time gives a good picture of reaction evolution for starting material and product. then it becomes really interesting. Using Blackman's approach to kinetic analysis, which reference is given later in this presentation, the authors investigated two well-defined sets of reaction conditions. Reaction B differs from reaction A by the ratio of reactants concentration versus catalyst concentration, as you can see on the table. And as you can see on the figure right below the table, the initial rate for the two sets of reaction conditions is the same, meaning that there is no catalyst deactivation of poisoning. If there were any deactivation of poisoning, reaction A, which has relatively less catalysts, versus reaction B, would show a slower reaction rate. The third set of experiments was conducted by varying the concentration of bromoalkyne 1, everything else remaining unchanged. And as you can see in the figure, this does not affect the initial reaction rate. This observation, together with the results shown on the previous slide, indicates that the reaction is zero order in both reactants. Now let's take a step back for a second and consider the implication. If you think in terms of catalytic cycle, it means, as we all know, that some steps are faster than others. And to be more specific, neither the bromoalkyne or the terminal alkyne are involved in rate limiting steps. Let's draw a picture to make it easier to understand. If neither the bromoalkyne or the terminal alkyne are involved in rate limiting steps, this leaves us with two positions in the catalytic cycle where the rate limiting step is to be found. A, condensation of intermediates 4 and 5 to give 6, or B, reductive elimination yielding the final product 3. In the interest of time and leaving the suspense intact, I like to stop here and invite you to go and read the paper. I thought though that this publication was very valuable, very interesting for the insight it gives us about the mechanistic nature of this particular cross-coupling reaction, thanks to a savvy use of online reaction analysis and well-planned investigation of reaction conditions. After a few more sets of experiments, it was finally found that the rate of the reductive elimination step was enhanced by the presence of ligand L1. Alright, I'd like to take advantage of this and give credit to Professor Donna Blackman and give the reference to one of her key papers listed at the bottom here. That paper summarizes Professor Blackman's approach to graphical kinetic analysis, and I would also like to let you know that Professor Blackman is going to present a webinar on this April 28th about this very methodology. And just to let you know, Metal-Toledo is right now about to release a software module that makes the preliminary kinetic assessment methodology available very easily so that organic chemists can use simple graphical manipulation of data to extract vital kinetic information in far fewer experiments than typically done using conventional kinetic methods. Alright, this is the fourth and last example of this metal-catalyzed reaction category. This is a fascinating paper from Jan Beckvall from the University of Stockholm and covers a popular area of research in organic synthesis, dynamic kinetic resolution catalyzed by ruthenium complexes. The paper was published last year in JACS, and even though ruthenium catalysts have been successfully used in combination with lipases to convert racemic secondary alcohols 2 into enantiopure acetates 3, and that's called dynamic kinetic resolution, or DKR, the same reaction doesn't work quite as well when using olefinic alcohol 4. It seems like alcohol 4 racemizes only slowly, and that's possibly because of coordination of its double bond to ruthenium. Indeed, the paper describes the use of NMR spectroscopy and in situ FTIR to show evidence for a ruthenium olefin complex. So now let's go into the details. When reacting allylic alcohol 4 and ruthenium complex 6, You can see two IR bands at 2021 and 1964 wave numbers coming down. They correspond to ruthenium complexes, and you can also see a new band coming up at 1982 wave number, and that's in the CO region. Similarly, a new peak is formed in the acid region at 1644. Trending those peaks allowed Beckvall and colleagues to notice that the rates of disappearance and formation were the same, which supports the hypothesis that diastereomers 10A and 10B are formed. In conclusion, I really like this example because it combines the gathering of structural clues based on the functional specificity of mid-infrared, but also kinetic clues based on in situ reaction rate monitoring. As a result, it was possible, thanks to in situ FTIR, but also proton and carbon NMR spectroscopy, to identify the formation of diastereomeric ruthenium complexes 10A and 10B, and therefore explains the slow rate of isomerization of 4, which makes 4 a poor substrate for dynamic kinetic resolution. I'd like to move now to the next chapter, which covers some examples of extremely useful polymerization reactions as described by Professor Donald Derensberg from Texas A&M in collaboration with EG University in Turkey. Some papers from Professor Derensberg have already been covered in a previous webinar that I listed here at the bottom. However, I thought it was critical to show some of the latest advances from Professor Derensberg because he's been amazingly creative and prolific in using carbon dioxide to produce polycarbonate. As you can see here on the screenshot from Chemical and Engineering News, taken from one of January's 2010 issue, Professor Derensberg received an award in inorganic chemistry from the American Chemical Society. I also would like to emphasize on the importance of using CO2 to make polymers and polycarbonates, as shown on this December's issue from Chemical and Engineering News, that mentions the seminal work from Professor Jeff Coates at Cornell that further evolved in the creation of the company Novomer. I would like to mention that some of the work with React-IR from Professor Coates at Cornell was summarized in a previous webinar, also listed at the bottom of the slide and available to you if you would like. Alright, the paper I'm interested in showing today covers the copolymerization of cyclohexane oxide and carbon dioxide in the presence of silane-chromium complex 1 and in the presence of a phosphine salt used as an initiator. The product from the reaction is polycyclohexylene carbonate, and you can see from the pictures on the right side that the polymer made with catalyst 1 definitely has a more appealing color than the one made with standard silane chromium chloride, which yellowish color comes from metal contaminants. Product formation was easily monitored by IR using the C double bond O absorption at about 1740 wave number. When trending this peak, you get a good idea of reaction profile and reaction dynamics. On the upper right corner, the figure shows you the rate difference when using either 0, 1 or 2 equivalents of phosphine salt. Actually, it appears that the reaction is slow when no initiator was used, but 1 equivalent is actually better than 2. There is some inhibition with 2 equivalents. Now it looks like not much is happening when no phosphine salt was present, but if you look at the bottom right, where the absorbance on the y-axis was expanded, you definitely see a rate profile indicative of an autocatalytic reaction, at least in the early stage of the reaction. What I really like in this paper is to show you how in situ reaction analysis can avoid the need for sampling when sampling is made difficult because of pressure. For instance, here, the system used by Professor Derensberg's team was a dedicated part pressure vessel, like shown on the picture, with the sensor technology directly mounted at the bottom of the vessel. Other technologies used and described in the paper are proton NMR and carbon NMR used to characterize polymer composition. Let me now move to the last example of this webinar series with this paper from Professor Charpentier from the University of Western Ontario in Canada. Professor Charpentier described the development of chemical reactions in supercritical CO2. To be more specific, the paper I am referencing here covers the use of in situ ATR-FTIR to monitor the formation of silicium, titanium and zirconium oxides using a salt gel methodology in supercritical CO2. I found this publication particularly interesting because of its emphasis on chemometric tools. So, for instance, when reacting TeOS with acetic acid, the monomer and the product peaks overlap with one another in the oxo region, as shown on the upper left three-dimensional view. In other words, what looks like a single band actually can be deconvolved into various peaks using chemometrics. Professor Charpentier's team used Simplisma, but actually Concert, now available in the React-IR software, could have been used as well. As a result, what looks like a hard-to-interpret waterfall plot provides two nice kinetic trends from the band at 1000 to 1100 wave number, one corresponding to silica and the other one to the monomer, as you can see on the right side of the slide. In addition, Simplisma as well as Concert give the mathematically calculated spectrum corresponding to the resolved pure components, as shown on the bottom left. As we just saw, these now resolved peaks can be trended over time, which allows to have a fast way to screen reaction conditions and get rates in real time. On the left side, you get a picture of reaction rates as a function of reaction temperature in the 40 to 60 degrees range. On the right side, you get an idea of sensitivity of rates to pressure in the 1300 to 3000 psi range. The formation of titanium oxide from titanium isopropoxide was investigated using the same approach. On the left side, you can see the overlap of the titanium acetate band with the ones due to the product in the 14 to 1600 wave number region. As shown on the upper right, chemometrics can deconvolve the various spectra, which allows to trend the concentration of the titanium acetate complex and the product concentration, as shown on the bottom right. And you probably noticed that compared with the previous kinetic profiles, these two ones really look steep around 2000 minutes reaction time. Looks like a very fast reaction actually once it gets started. I'm going to stop here. There is much more to show than I have time to present, and I really encourage you again to go and read the paper. It's really a great publication. I wanted to include this paper in the webinar because it's one of the relatively few examples showing the use of React-IR for salt gel chemistry and more generally for chemistries under supercritical conditions. The outcome of the study was to be able to rank the various oxides in terms of reactivity and get a good idea of reaction dynamics. For instance, as you can see on the bottom left, the conversion of zirconium butoxide follows a smooth conversion profile on the left, but the decrease of titanium isopropoxide follows a sharp, steep curve instead. And I also like the use of chemometrics because it shows you that you should not be discouraged to use React-IR even when dealing with very complex molecules, as today's computers allow to take full advantage of chemometric tools and resolve challenges that were perceived as daunting not even 10 years ago, and they are now fairly easy to deal with. With this, I'd like to conclude my presentation, giving you a few more references of recent papers published by academic researchers, which I think are really worth reading.